now that we've reviewed the basics of set theory, we're going to spend the next couple of weeks looking at probability and measuring in particular the probability of outcomes of what are called random experiments. So these are experiments where the outcome is truly random. They don't yield the same result no matter how carefully they're performed. All right, so things like rolling dice, flipping coins, these are random experiments. And perhaps the most fundamental object that we'll be introducing and studying today is when we perform an experiment, we have the sample space. So the sample space of the experiment is a set of all possible outcomes. So for example, something like rolling a six-sided die, what are the possible outcomes? Well, you either roll a 1, a 2, a 3, a 4, a 5, or a 6, right? So the sample space, which we'll pretty much always denote with an uppercase S, the sample space of this experiment is 1, 2, 3, 4, 5, or 6. Alright, here's another one, flipping a coin. Well, what happens when you flip a coin? You either get a heads or a tails, right? So the sample space in this case, flipping a coin, is a 2-element set. It's just heads or tails. And flipping 2 coins, well now slightly more complicated. Here's the notation I'll go with. We use H and T for heads and tails again, but my sample space is, okay, I either flip 2 heads, so I'll denote that outcome with HH, or the first coin is a head and the second coin is a tails, so HT. Or, and this is a different outcome, the first coin is a tails, the second coin is a head, so this would be TH. Or they're both tails, so I'll denote that by TT. Alright, so these are the sample spaces for these 3 experiments we've listed. It's the set of all possible different outcomes. Full disclosure, these are somehow very fundamental sample spaces. Coming back to this example, something like rolling a 6-sided die, you could say my sample space is just going to be, maybe all I care about is not the number that I see on the die, the number of pips, but maybe I just care about if I roll an even number or an odd number. And this is okay as long as you're 100% sure that that's really all that you need to know to continue on with your investigation of whatever you're looking at. Alright, so in general I would recommend taking the most sort of fundamental sample space that you can with the largest number of elements, right? You really want to record every single possible outcome unless you're 100% sure that you don't need all of that information. Alright, somehow this is more coarse than this one is. So in general, I will be taking as large of a sample space as possible, really measuring every single possible outcome. Alright, so just introducing a little bit more terminology that I've already written up here behind me, we have subsets of S. So S is again the sample space, the space of all possible outcomes. Any subset of S is called an event, and I'll usually denote these subsets by E, so E for event. And the simple events are just 1-element subsets, so they're actual outcomes. They're outcomes of the experiment. They're simple outcomes. These are simple events. Meanwhile, a compound event is any subset with more than 1 element. So for example, coming back to rolling a 6-sided die here, the event that corresponds to this thing, the outcome is an even number, would be, well, our sample space is 1, 2, 3, 4, 5, 6, right? Coming back to rolling die. So the event that corresponds to this would be the subset of all even numbers of S. So you either roll a 2, a 4, or a 6. Alright, so this is a compound event, but it's a subset of S. So any subset of S is called an event, and you can usually describe them with words. So this event, rolling a 2, 4, or 6, would be the event corresponding to you roll an even number. Alright, so now we want to jump into probabilities. So probabilities. We're interested in measuring the probabilistic outcome of a certain event when we perform an experiment. So we need a definition for this. How do we define what is a sort of an acceptable probability measure? So here I have a sample space for my experiment. It's just it's a bunch of simple events, E1, E2, out to En, so n different possible outcomes here. And to each of these events we assign a real number that I've denoted by P of E sub I. Think of this as a function if you want to get really fancy with it. You plug in the event into this function P, and you output a number. And this real number that it outputs is called the probability of the event E sub I, And we have to have a few conditions on this. One is my probability of each event has to be between 0 and 1. Think of 0 as being 0% probability, 1 as being 100% probability. So it has to be somewhere between those two numbers. And secondly, when I add the probabilities of every single possible outcome, the sum of all of the possible outcomes should sum up to 1, right? Because one of these events is going to occur when we perform the experiment. So they should all, when you add them all up, all of the probabilities should add to 1. And so there's our definition of a probability function, but I want to jump straight into an example because it's a lot easier to understand this when you're working with actual experiments. We're going to return to the 6-sided die example again. So we're returning to this experiment, and our sample space is once again all the different possible outcomes. You either roll a 1, a 2, a 3, a 4, a 5, or a 6. And I want to assign probabilities to each of these outcomes. Well, assuming it's a fair die, then each outcome should be equally likely, right? So if the die is fair, it is reasonable. It's reasonable to assign the probabilities probability of rolling a 1. I have 6 different possible outcomes, so if I'm going to assign them all the same probability, probability of rolling a 1 would be 1 out of 6, 1/6. Probability of rolling a 2 would be 1/6. Probability of rolling a 3 is 1/6. Probability of rolling a 4, 1/6. Probability of rolling a 5 is 1/6. And probability of rolling a 6 is 1/6. And I want to point out that this satisfies our properties of being an acceptable probability function. Every single probability is between 0 and 1. And when I add the probabilities of every single possible simple event, when I add the probabilities of all of these, 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, that equals 1. Right? So they sum up to 1. So this is an acceptable probability function. And we'll do some examples. What is the probability of rolling a 5? Well, you can actually just read it off here, right? The probability of rolling a 5 is, by my probability function, is 1/6. So, probability of rolling a 5 is 1/6. But let's do something more tricky. How about what's the probability of rolling an even number? And so B what is the probability of rolling an even number? And this is where events come in. This is where you want to make an event for this. So what's the event corresponding to roll an even number? Well, the event would be you either roll a 2, a 4, or a 6. So we're asking, what is the probability of this event? And it turns out to find the probability of an event, you just have to add up, take the sum of the probabilities of every single simple outcome in that event. So it's actually just going to be the sum of the probability of 2 plus the probability of rolling a 4 plus the probability of rolling a 6. So that is 1/6 plus 1/6 plus 1/6, which is 3/6, or 1/2. So let's make a note of that, because this is sort of one of the most basic facts to know about probabilities and probabilities of events, is the probability of E is the sum, any event now, is the sum of the probabilities of every simple outcome. How about I just say probabilities of every element of E? we'll use actual set terminology, every element of E. But every element of E is a simple outcome of the experiment. Alright, so with that in mind, let's do one more example. How about what is the probability of rolling, here I just leave most of this on the board. What is the probability of rolling a number less than 3? Probability of rolling a number less than 3, okay, so what's this event correspond to? Well, this means my event would be I either roll a 1 or a 2. So pretty bad squiggly bracket there. So my event is I'm either rolling a 1 or a 2, and the probability of this event is the sum of the probabilities of rolling a 1 or rolling a 2. Each of these has a 1/6 chance. This is 1/6 plus 1/6, which is 2/6, or simplifies to 1/3. Alright, well let's make this a little bit more complicated. This formula is a formula we'll use forever, but let's suppose our die isn't a fair die. Let's suppose it's weighted. So we'll have different probabilities for each outcome. And so we wanted to test if our die is actually fair. We assumed it was when we assigned these probabilities of 1/6 to each possible outcome. But suppose we actually tested and we roll this die 1,000 times and we get the following results. We find that we roll a 1 only 52 times out of 1,000, 2 120 times, 3 123 times, 4 106 times, 5 114 times, and 6 485 times. So it certainly doesn't look like our die is fair. It's possible we just got very unlucky, but also extremely, extremely unlikely. So it looks like this is a weighted die that's heavily weighted to favor rolling on a 6. Alright, so based on this evidence, we assign different probabilities. We no longer assume we're going to roll a 1, 1/6. The probability of rolling a 1 is 1/6, probability of rolling a 2 is 1/6, and so on. We're going to take this data and use this to assign probabilities. So we assign the probabilities to the simple events in S as probability of rolling a 1. Well, it looks like it should be 52 out of 1,000, or 0.052. Probability of rolling a 2, looks like it's probably 120 out of 1,000, so 0.120. Probability of rolling a 3 is 0.123. In fact, let me write this over here so we can keep this on the board. 0.052. 0.120, probably rolling a 3, what was that? 123 out of 1,000, so 0.123. Probability of rolling a 4 is 106 out of 1,000, 0.016, or sorry, 0.106. Probability of rolling a 5 should be 0.114. And probability of rolling a 6. We got 485 out of 1,000, so 0.485. Alright, so earlier we assigned probabilities using a theoretical approach. We just assumed every outcome was equally probable, so theoretically our probabilities should have been 1/6. Alright, so earlier we took a theoretical approach to assign our probabilities, but now we're assigning probabilities based on what's usually called an empirical approach. We are using the empirical data from an experiment and using that to assign our probabilities, right? So this is the empirical approach. And there's nothing wrong with either. Usually throughout our study of probabilities, we'll just be going with a theoretical approach, but sometimes you have empirical data that you can use to assign probabilities instead. And if that empirical data is radically different than your theoretical suggestion, then you would use this data instead, as we're doing here. There's a really interesting result in mathematics. It's the law of large numbers that says that, okay, this might not be the exact probability based on this die of rolling these numbers, or sorry, these probabilities might not be the exact probabilities, but the law of large numbers says that as long as you take a very large sample size, in fact, by taking a larger and larger sample size, you can make the empirical data that you get arbitrarily close to the true probability. So 1,000 is pretty big. 1,000 is a pretty big number, so I'm assuming that these probabilities are in fact very, very close to whatever the true probability is. If I wanted it to be even closer, if I wanted to be sure that I was even closer, I could roll it 10,000, 100,000, 1,000,000 times. And as I increase the sample size, the law of large numbers says that the probability that we measure should be getting closer and closer to the true probability. So I think we'll have something to say about the law of large numbers, maybe in the next section. But for now, just be aware that as long as you perform many, many of these experiments, the empirical data that you have should be very close to the actual true probability. So anyway, I was going off on a tangent there. Let's do some probabilistic calculations. So we have this die, we assume it's weighted, and these are the probabilities that we're assuming is about the probability of rolling each of these numbers. So, for example, once again, what is the probability of rolling a 6? Well, my event is just one element, it's a 6. So the probability of this event is the sum of the probabilities of each occurrence or each element in the event. So this is just the probability of rolling a 6, which is 0.485. Okay, so there's one. How about what is the probability of rolling a prime number? Probability of rolling a prime number. So what's this event correspond to? If I roll a prime number, then I've either rolled a 2, a 3, or a 5. So the probability of this event would be the probability of rolling a 2 plus the probability of rolling a 3 plus the probability of rolling a 5. And now I just have to add them up. Again, before we just assume these are all 1, 6, but now using some empirical data, we're going to go ahead and say, okay, my probability of rolling a 2 is 0.120. Probability of rolling a 3, 0.123. Probability of rolling a 5, 0.114. And what do these add up to? This is 0.243, 343, 353, 357, I believe. This is 0.357. Yes. Or 35.7% if you prefer percentages. But when we talk about probabilities, we'll talk about numbers between 0 and 1. So probability of rolling a prime number for this die is 0.357. Again, still not all that likely because it's heavily weighted towards rolling a 6. Let's just do one more example, and I'll introduce one more formula, although we've sort of already been using it. Alright, so suppose we flip a coin 3 times. Then what's my sample space going to be? Sample space, well, I either get heads 3 times in a row, so heads, 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 or I get heads, heads, and then a tails, or I get heads, tails, heads, or there's quite a bunch of outcomes here, heads, tails, tails, or yes, or I get tails, heads, heads, or tails, heads, tails, or tails, tails, heads, or tails, tails, tails. In other words, I'm writing down all the possible permutations of heads and tails, just choosing 3 of them, and making sure I have them all right. So once again, I've got 2 choices for the first slot, either heads or tails, then 2 choices for the second outcome, then 2 choices for the third, so I should have 8 total permutations, and I think I have 1, 2, 3, 4, 5, 6, 7, 8. 8 different permutations, so I do indeed have all of them. And what's the probability of each event going to be? Well, theoretically, we would assume every single outcome is equally likely, right? Because our coin is equally likely to roll or land either on heads or tails. So we'll assume that our probability of each outcome, so this would be the probability of heads, 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 probability of heads, heads, tails, and so on. Probability of each outcome would be 1/8, right? Because there's 8 total possible outcomes. Each one should be equally likely, so 1/8. And by the way, when you do this, when you assume that every single outcome is equally likely, this is usually called the equally likely assumption. So I had this sample space with the equally likely assumption. And we'll just do some probabilistic calculations. So what is the probability of 2 or more heads? Maybe I should say of flipping or seeing or something, of flipping 2 or more heads. Well, let's figure out what event this would be. So seeing 2 or more heads, HHH counts, so HHH is fine, that would be in this event. So is HHT. So is HTH. HTT is only 1 head, then I've got THH. And I think that's it. This is only 1 head, 0 heads. Okay, so the probability of flipping 2 or more heads, this is the event we're looking at, and the probability of this event is just going to be probability of HHH, which is 1/8, plus probability of this guy, 1/8. They're all 1/8 probability, so 1/8 plus 1/8 plus 1/8 plus 1/8, which is 4/8 or 1/2. But I want to point out that there's a small time-saving device here, which is instead of writing out 1/8 plus 1/8 plus 1/8 plus 1/8 every time, notice what I have up top here. Up top, I have a 4. What is 4? It's the number of elements in E. Right, so 4 is the number of elements in E. And what is 8? How did I get 8? Well, because we assume the equally likely assumption, every outcome had a probability of 1 over 8, where 8 was the number of elements in the sample space. So this is just the number of elements in E over the number of elements in S. And this formula can save you some time. Instead of writing down this stuff, understand that when you're working with a sample space where you've assigned this equally likely assumption, when you're finding the probability of an event, this is all you really have to calculate. It's the number of elements in the event over the number of elements in the entire sample space. So probability of E is n of E over n of S. If we have the equally likely assumption. Alright, so really important. So we'll just do one more example, I suppose. We'll still work with the same sample space. Maybe I shouldn't have erased my sample space. Let's see if I can recover it. HHT, I believe I only erased one term. H. Okay. Is that still 8? Yes. So B, what is the probability? What is the probability of flipping exactly 1 tails? Alright, well let's figure out the event that corresponds to this. How many ways can I get exactly 1 tails? I could do, I could flip an HHH, or sorry, HHT rather, HTH, or THH. So those are the only permutations that have exactly one tails, and therefore the probability of this event is, well, there's 3 elements in E, so 3 over the total number of elements in the sample space, 8. Using this formula over here because we have the equally likely assumption. All right, let's just do one more very quick problem, but we're basically done with this section. We'll call it C. And how about this? What's the probability of 4 heads? Alright, so what's the event that corresponds to this? How many of these outcomes have 4 heads? Well, none of them, right? So the event is the empty set. And therefore, the probability of this event, well, adding up the probabilities of everything in E, 0, or using this formula, the number of elements in E is 0 over 8, or just 0. Alright, so there's all of the principles from this section. The sample space of a random experiment is a set of all possible simple outcomes. And to those simple outcomes, we assign a probability function. To every single outcome, we've got a probability assigned to it. That probability has to be somewhere between 0 and 1, and has to satisfy that the probability of every single outcome when you add them together should equal 1. But we've got our sample space, all the outcomes, probabilities assigned to them, and if you want to know the probability of an event, which is a subset of the sample space, if you want the probability of an event, you just have to add up the probabilities of every single simple outcome in that event. Okay, so you'll see lots more examples for homework, but the principles are the same, just different experiments. Thanks.